Okay, another question here. System of linear equations is given here. x1 plus 2x2 plus 4x3 equals minus 2. x2 plus 5x3 equals 2. Negative 2x1 minus 4x2 minus 3x3 equals 9. Find the reduced echelon form, and then to check if this linear system is consistent. If it is, write down the parametric vector form. Okay, so it's 1, 2, 4, negative 2, 0, 1, 5, 2, negative 2, negative 4, negative 3, 9, right? So this is the augmented matrix. And what we can do here is can use the row 3, right? Plus 2 times row 1. Let it to be the new row 3. So you're going to have 1, 2, 4, negative 2, 0, 1, 5, 2. So this part becomes 0. This part becomes negative 4 plus 4 is 0. This is going to be 5, right? This part is going to be also a 5. Okay, also a 5. Okay, so I think right now should be very, very close, because if you continue to do the reduce, 2, 4, negative 2, 0, 1, 5, 2, you're going to have a 0, 0, 1, 1, right? And if we do use row 2, minus 5 times row 3 becomes new row 2. So that gives us this 1, 2, 4, negative 2. We're going to have it 0, right? 1, 0. So it's going to give us this negative 3, 0, 0, 1, 1, right? And then you can do use the row 1 minus 4 times row 3 becomes a new row 1. That will give us this 1, 2, 0, right? So it's going to be minus 6, right? And that minus 2 minus 4 is minus 6. 0, 1, 0, negative 3, 0, 0, 1, 1. And you can use row 1 to minus 2 times row 2 becomes new row 1. So it's 1, 0, 0. So this part is negative 6 minus negative 0. So it's 0, 1, 0, negative 3, 0, 0, 1, 1. So this is the reduced echelon form. And clearly, if this system is consistent, so this is part A. Part B is consistent. The answer is yes, right? And the solution is easy to write it down, right? x1 equals 0, x2 equals negative 3, x3 equals 1. So the solution, okay, so that's it. Easy stuff. Number 4. So given this is true, observe that the first column minus 3 times the second column equals the third column. Find a non-trivial solution of this. Well, for this one, if we denote this is column A1, column A2, column A3, and noticing that is the first column minus 3 times the second column equals the third column, right? But for this non-trivial solution, we actually are looking for what is x1a1 plus x2a2 plus x3a3 equals the 0. Of course, this part is going to be vector, right? 0 vector. If it's non-trivial, that means that at least one of the x is going to be non-zero. But look at what we have. We have a1 minus 3a2 minus a3 equals the 0 vector. So don't you agree that you can let your x1 equals 1, x2 equals -3, x3 equals -1, right? So you see a non-trivial solution is going to be 1, -3, -1. This one is also super simple. Okay. Now, next question. So giving all of this, right? So determine. So you have v1 is -1, -3 is 0. v2 is -3, 7, 1. v3 is 3, -1, -4, and v4 is -2, 2, and 3. It asks us a few questions. First one is it asks us if this v3 is in the span of this v1 and v2, right? v1 and v2. Okay, so we can easily check that. Okay, we can easily check that. So meaning we want 1, -3, 0, -3, 7, 1, and then it's a 3, -1, -4, right? -4. So basically what we are doing here is we're trying to know that if there is a solution or not for this augmented matrix, right? So that's the main task. Okay, that's the main task here. So what we can do? Well, as you can see here is if we do a row 2 plus 3 times row 1 becomes the new row 2, you're going to have the 1, -3, 3, right? So this part becomes 0. This becomes -2. This becomes into, so -1 plus 9 is 8, right? 0, 1, -4. And then you can see that actually you can use the row 3, to and plus half of row 2 to become the new row 3, right? And then easily you will see that this part will become 0. So it's 1, -3, 3, 0, -2, 8, and 0, 0, 0. Okay. So after here, we actually solve this one easily. So, right. So if you do one more thing, so it's 1, -3, 3, 0, 1, -4, 0, 0, 0. So if you so just use row 2 divided -2 becomes new row 2. And then you can use row 1 to plus 3 times row 2. That will give you it's 1, 0, right? So 3 times row is -12. So this is going to be -9. So 0, 1, -4, 0, 0, 0. So clearly you can see that x1 equals negative 9 and x2 equals negative 4. In other words, we can write v3 as a negative 9 times v1 minus 4 times v2. So if it's in the span, the answer is yes. Okay, so that's part A. Part B is if this v1, v2, oh, excuse me, it's just if it's v2, v3, v4, those are linearly independent, right? So to do that, we actually are looking for is this negative 3, 3, negative 2, 7, negative 1, 2, 1, negative 4, 3, 0, 0, 0. If it has a only has the trivial solution or not. If it has the only trivial solution, then we can claim that v2, v3, and v4 are linearly independent. Otherwise, noticing that it will be the non-independent. Okay, so we can do a few things, right? We can do a few things. So as you can see, the first one, what we can do is we can use row 1 divided by negative 3, right? To becomes new row 1 to rescue it. So it's 1, negative 3, and of course this part of 2/3, 0, 7, negative 1, 2, 0, 1, negative 4, 3, 0 here. Okay. If you continue to do that, so you can use the row 2 minus 7 times row 1 becomes new row 2, and use row 3 minus row 1 becomes a new row 3. So it's a 1, negative 3, 2/3, 0. So this part becomes a 0 here, right? 7, so this card becomes into 20, right? Because negative 3 times 7 is negative 21. You might say it become plus that. This negative 1 plus 21 is 20. So this part times 7. Okay. So it's a 2 minus. So let me do a little bit more calculation here. So it's going to become a 2 minus 14 over 3. This part becomes 6 over 3 minus 14 over 3, so it's negative 8 over 3. Okay, so that's negative 8. It's negative 8 over 3, 0. So this part, it's 3 minus 5, so it's a 0 here. This is going to become negative 1. And this part, 3 minus 1 is going to give us this is 7 over 3, and then 0. Okay. Now, of course, you can continue to do a lot of things here. There's one thing you can do is you can use this row 3 plus 1 over 20, right, times row 2. So you see it's a negative 3, 1, negative 3, 3 half a 0, so it's a 0, 20, negative 8 over 3, 0, so it's about 0, 0, and so for this part, we can do another round of calculation here. So it's 7 over 3 plus 1 over 20 times negative 8 over 3. Okay. So as you can see, this part is 2, this is 5. Okay. So it's a 7 over 3 minus 2 over 15. And we can do 35 over 15 minus 2 over 15. So give us the 33 over 15. Okay? So this part is going to be 33 over 15 here. Okay, 15 here. Up to here, I think we should be good to go. Why? Because apparently from row 3, you drive that, x3 is going to become 0, right? Because this one times x3 is 0. So we got 0 here. And then 20 plus this part 0 give us 0. You can drive that x2 also equals 0. And then with x2 and x3 are 0, don't you agree that you also get that x1 equals 0? Okay, so yes, this solution has the Olin trivial solution, had the Olin trivial solution. Okay, and hence those V2, V3, V4, these are linearly independent. The answer is yes. Okay, this is also yes. Okay, well, that's part B. Part C, it also is V1, V2, V3, V4 are linearly independent. Well, I think we need another new page to work on this, right? This is linearly independent. Well, this is equivalent to ask us to do 1, 3, negative 3, 3, negative 2, negative 3, 7, negative 1, 2, 0, 1, negative 4, 3, 0, 0, 0, right? It asks us to, is this linearly independent or not, right? So it asks us. So we can definitely do this way, and then to do this to reduce this augmenting matrix, and then we can do that. Okay, we can do that. And but if you look at this one again, okay, so noticing that we also have one of the theorem. It says like into this. So it says like this. So if you have a set, okay, it contains small vectors, okay, then the entries in each vector, then that set is linearly dependent, right? So there is one of the theorem says like this. Okay. So if we look at it here, you see this set V1, V2, V3, V4. We have 4 of them, right? But the number of the entry in each vector, it's 1, 2, 3, so it's the 3. So 4 is greater than 3. So hence, based on this theorem, we can immediately get that those set in R3 is linearly dependent. Okay, so the answer for this one, actually we don't need to perform this, but rather we can, based on this theorem, have then to drive there. Okay, so that's this one.